Did you know that some stars grow so enormous that they could swallow our entire solar system and still have room to spare? You're drifting, now weightless, far from the little blue world you once called home. The ship around you is quiet, humming with that soft engine lull that almost feels like breathing. The recycled air brushes your skin, warm and steady, and the faint vibration under your feet reminds you that you're moving fast. Outside the window, darkness stretches in every direction, a black ocean scattered with cold, distant stars. But tonight, you're searching for one star in particular. Not just any star, a giant, a monster swollen with heat, age, and impossible scale. A star so big it feels unreal, like something that shouldn't exist, yet does. As the ship glides forward, you feel a gentle tug in your stomach, gravity shifting, reminding you you're truly out here. And as you settle into the seat, you catch yourself wondering, what happens when a star grows too big for its own good? How do you even measure something so huge it barely holds itself together? Out here, in the quiet between constellations, those questions don't feel like science, they feel personal. You're close enough to imagine the heat, the trembling layers of gas, the final breaths of a dying giant. This journey will take you through that story, from a star's violent birth to its massive, unavoidable collapse. Some stars don't just shine, they swell, they strain, they break the rules, red, hot, bloated, trembling against gravity's grip. These are the hypergiant, largest objects we've ever known. Names like Stephenson to 218, Ui Scuti, and Vi Canis Majoris drift through your mind as the ship moves deeper into the dark. These aren't stars you've ever seen with your own eyes. They hide behind dust clouds and far-off clusters, invisible from Earth. But astronomers have peeled back those shadows with infrared eyes and delicate measurements, revealing titans beyond imagination. Take Stephenson to 218, a massive red supergiant near the constellation Scutum. It might be the largest star ever found, its radius so enormous that our entire solar system could vanish inside it, with room left over. Hard to picture, isn't it? That space for you always bigger than your best guess. But estimates suggest it could be over 2,000 times wider than our sun. Then there's Ui Scuti, once the reigning champion, dwelling roughly 9,000 light-years from us. Its estimated radius also comfortably exceeds 1,000 times that of our sun. And Vi Canis Majoris, an elder statesman of giants, cloaked in swirling dust, offers us a quiet, sobering glimpse into the eventual decay of stars. These celestial behemoths aren't necessarily the heaviest stars. Their mass doesn't always outweigh every other star, but by volume, by their sheer physical expanse, they are without question the true, undisputed giants of the entire cosmos. A humbling thought, isn't it, as the starlight reflects softly across the viewport? But truly, what does it genuinely mean to be 2,000 times larger than our sun? These sorts of comparisons can feel so abstract, almost impossible to visualize. Our own sun, after all, is already an enormous entity. You could line up more than 100 Earths across its diameter. Yet these hypergiants would shrink it to utter invisibility. Imagine for a moment replacing our sun with Stephenson to 218. Its scorching red surface would billow out beyond the orbit of Saturn, a blazing rust-red globe that would effortlessly swallow every single planet from Mercury all the way past Jupiter. Even you, Ui Scuti, slightly less immense, would still engulf our entire inner solar system, stretching well beyond Mars and halfway towards the distant gas giants. Can you imagine gazing skyward, only to see the horizon dissolve into an unending wall of glowing, ruddy gas? From our current vantage point, here in the serene quiet of the ship, we wouldn't see a sky at all, merely the pouring atmosphere of a distant, dying titan filling our entire view. The scale isn't just vast, it's profoundly alien. These stars don't possess a surface in the way our planets do. Their outermost layers are so incredibly diffuse, so stretched by intense heat and the sheer pressure of light, that the boundary between star and the surrounding space becomes a hazy, beautiful twilight zone. The density near the very edge can be thinner than the air you're breathing right now, yet it remains fundamentally part of the star. You could, quite literally, drift for hours, perhaps even days, through the wispy upper atmosphere of a hypergiant before encountering anything resembling its denser inner structure. All the while, you'd be enveloped by plasma, ionized gas, glowing with the light from the furious heart deep within. Even though our human minds grapple with such mind-boggling scales, astronomers have, with quiet ingenuity, devised elegant ways to measure them. By carefully analyzing the gentle fluctuations in their light, the specific infrared emissions, and the unique spectral absorption features of these incredibly distant objects, we can estimate precisely how vast they must be to generate the kind of luminosity we observe. These complex calculations are always evolving, of course. Margins of error are understandably large, and wispy dust clouds can often obscure parts of the true picture, but the overarching narrative remains remarkably consistent. Some stars, it turns out, truly are this magnificent and enormous. They live fleetingly, radiate with furious intensity, and eventually dissolve into a spectacular final collapse. As we begin to quietly explore how these giants came into being and why they're already nearing their demise, it's worth remembering that sheer size alone doesn't guarantee survival. In fact, for stars like these, being this incredibly large is very often the dramatic prelude to their eventual end. When astronomers undertake the incredible task of measuring the sheer size of a star, especially one located thousands of light years away, they aren't directly measuring anything in the way you might use a ruler. There are, after all, no cosmic measuring tapes, and certainly no way to perceive these distant stars as clear, distinct disks with sharply defined edges, not with our conventional telescopes, anyway. Instead, scientists rely on a clever combination of the star's apparent brightness, its temperature, and its precise distance from us. By meticulously studying how much energy a star emits across various wavelengths, visible infrared, and occasionally ultraviolet, and then comparing that to its measured distance from Earth, they can accurately estimate its overall luminosity. Then, using fundamental principles of physics, they meticulously calculate just how large the star would need to be to produce that immense amount of light at its observed temperature. The result is a radius, not measured in kilometers, but in solar radius multiples of our own sun's familiar size. This method, while brilliant, is far from straightforward. To estimate a star's radius with any degree of accuracy, astronomers must first know its exact distance, which often comes from precise parallax measurements taken over many months or even years. They also need to, as our vessel glides silently through the cosmic tapestry, a soft, almost imperceptible vibration resonates gently through the hull. You might notice that discerning the true nature of these distant suns is a subtle art. Interstellar dust, like a fine, shimmering veil, can play tricks on our eyes, sometimes dimming a star's brilliant light or scattering its glow, making it appear a little cooler or perhaps a touch smaller than its colossal reality. And some of these magnificent red hypergiants, you see, possess atmospheres so vast and mutable that their very size isn't fixed, but rather a slow, majestic breath, constantly shifting. Yet, even with these celestial deceptions, by carefully studying their unique light signatures and applying our most intricate models of stellar architecture, we can arrive at surprisingly consistent estimations. Nothing to worry about, probably. The light journeying across the void tells a profound story, a narrative written in truly unimaginable scale. Even for the most seasoned cosmic cartographers, the sheer numbers can be profoundly difficult to internalize. A star that stretches across a radius 1,000 times greater than our own sun doesn't just sound large, does it? It genuinely bends the very fabric of imagination. So, let's try to anchor that scale, to make it a little more tangible for you as we drift. Our sun's radiant heart extends to about 700,000 kilometers. Now, multiply that by 1,000. We're talking about 700 million kilometers a distance, far enough to reach well beyond the comforting orbit of Jupiter. Imagine, for a quiet moment, if such a star were to replace our familiar sun right now. Mercury, Venus, Earth, and Mars, all of them would be utterly consumed, not merely incinerated, but fully absorbed into its turbulent, gaseous outer layers. Even colossal Jupiter might find itself orbiting just asterisk inside asterisk its visible surface. The recycled air within our cabin feels constant, yet you might sense a subtle shift in the ship's balance as you ponder this. This isn't theoretical. This is real, observable, and it's both humbling and astonishing. Can you picture it? Our entire orbital journey around the sun, that full year-long passage tucked neatly within the vast, fiery limb of a supergiant star. You wouldn't witness a familiar sunrise or sunset. Instead, the sky would be a constant, breathtaking glow, awash in rich reds and molten golds, the very atmosphere gently pulsing with the immense tides of convection and radiation pressure. Day and night would simply vanish, swallowed by perpetual dawn. Our sun wouldn't be a distant dot. It would be a boundless horizon of burning clouds, rising on every side. For a planet like ours, life, as we know it, would be utterly impossible. But from a safe distance, from right where we are now, the sight would be beyond beautiful, a true masterpiece of cosmic artistry. Isn't that just like space? To help us grasp these non-human proportions, astronomers often resort to playful analogies, hoping to bridge the gap between concept and comprehension. Perhaps it helps to think of it this way. If our sun were the size of a basketball resting gently on the console, a star like Scuddy would be a vast sphere, nearly 60 meters across the length of a full passenger jet. And if Earth were a tiny pea orbiting that basketball, it would find itself far outside the boundaries of that jet-sized hypergiant, swallowed many times over. Or, let's flip the metaphor. If Earth were but a marble, and we placed it next to a star the size of an entire redwood forest, that might begin to approach the scale we're truly dealing with. These comparisons are imperfect, of course, but they offer a quiet moment of perspective, don't they? It might surprise you to know that these titans aren't rare or isolated cosmic anomalies. Red supergiants and hypergiants exist throughout the swirling arms of our own Milky Way galaxy. Most of them are transient, massive stars that have reached a spectacular, late stage of their stellar evolution. They don't stay this enormous for long. In fact, Their immense size is intrinsically linked to their very instability. The same powerful forces that compel them to expand, the relentless outward push of radiation pressure, the fiery output of fusion, the internal turbulence are precisely what also lead them inexorably toward their dramatic collapse. And soon, that final collapse will inevitably come. A cosmic sigh, perhaps. Not all enormous stars are cut from the same cloth. As we ponder these giants, we enter a vast spectrum, one that ranges from the modestly large to the truly extraordinary. At one end, we find the red supergiants, like the familiar ruby-red point of Betelgeuse in the shoulder of Orion, whose light drifts across the void to us now. These are stars that began their lives several times more massive than our Sun and have now, in their grand old age, expanded dramatically. Red supergiants are common endpoints for stars between about 10 and 20 solar masses. They are cool on the outside, luminous from within, and often shrouded by drifting, expelled clouds of gas, marking a temporary, swelling, trembling stage before their final, magnificent bow. But then we have the hypergiants, a distinct class altogether. These are not merely larger, they are fundamentally more unstable. A hypergiant is a star that has not only swollen to an incredible size, but also exhibits profound signs of severe atmospheric instability. Its outer layers aren't held neatly in place. Instead, they pulse, flare, and shed mass in powerful, violent outbursts. They often display peculiar spectral anomalies, generate furious stellar winds, and create complex, ever-changing circumstellar environments. The distinction between a supergiant and a hypergiant isn't just about how big it is. It's profoundly about its behavior. A red supergiant might swell and dim gradually, but a hypergiant, it might do so violently, shedding the equivalent of Earth's mass in gas every few years. Why does the universe always do this to you, showing you something even grander? The sheer, breathtaking size of these stars is the result of a delicate and ultimately temporary balance. Deep within their cores, nuclear fusion furiously pushes outward a constant, explosive expansion driven by the intense heat of atoms colliding and fusing into heavier elements. Yet, surrounding that incandescent core is the relentless inward pull of gravity, exerting immense pressure. In a stable star, these two opposing forces exist in a harmonious equilibrium. But in a massive star nearing the culmination of its life, that balance becomes profoundly unstable. The star has burned through its initial hydrogen fuel and now fuses heavier and heavier elements in layered shells, much like the intricate rings of an onion. This process creates complex zones of immense pressure, causing the outer layers to expand far beyond their original, more compact boundaries. As fusion continues, progressing into heavier elements like helium, then carbon, oxygen, and beyond, the energy output within becomes even more extreme, though paradoxically less efficient. The inner core contracts, heats up even further, and shifts to new, more exotic fusion stages. The outer layers, meanwhile, balloon outward in a direct response to this escalating internal pressure. These expansive outer zones become incredibly diffuse and tenuous, stretching into near vacuum conditions that barely cling to the star's weakening gravitational pull. That's precisely why a hypergiant can grow so incredibly vast, not because it's a solid object simply swelling like a balloon, but because its outer plasma is being gently yet powerfully lifted outward by immense radiation and thermal pressure. Imagine it, almost like a breath held too long, reaching out, trying to touch the void. In these incredibly expanded states, the density of the star's outer envelope can be unbelievably low. You might be surprised to learn that a cubic meter of space near the visible surface of a hypergiant could contain fewer particles than the air inside a quiet room right here on Earth. A startling thought, isn't it, as the console lights reflect the distant starlight? Yet, despite this almost ghostly tenuousness, it still glows. It still radiates its magnificent energy across the cosmos. It still counts. You find yourself now, perhaps without quite realizing it, drifting through the very breath of a star. Imagine a cosmic fog, not cold and damp, but radiating with an almost unimaginable heat, a gentle, fiery mist that stretches out endlessly around our quiet little vessel. Those shimmering light particles you see reflecting off the distant hull or dancing across the console's soft, muted glow aren't just starlight from afar. They are the very essence of this giant. A subtle vibration hums through the floor beneath your feet, a deep, resonant thrum from the ship's engines, barely audible above the whisper of recycled air, yet it reassures you that we are stable for now. From a distance, it appears a magnificent, solid orb, a beacon of pure energy. But up close, within these outermost ghost-like layers, it's a constant, churning dance. The star's surface is never truly still. It's a colossal ocean of hot gas, always in flux, like immense bubbles, rising from unimaginable depths, pushing outwards, creating subtle shifts in the ambient light. You might notice a fleeting brightening, then a softening, as these currents break through. Occasionally, this turbulent giant even sighs, expelling great arcs of its atmosphere into the void. Material that drifts nearby, glowing faintly in the infrared, a serene testament to its restless energy. Nothing to worry about, probably. These aren't random tantrums, you understand. This constant motion is the star's natural response to its own immense power, a cosmic struggle to contain itself as it swells and grows. It's reaching a limit, a fundamental threshold, where its own internal forces strain against its structure. And when that limit is truly met, a new chapter in its story begins, moving beyond mere expansion. It starts, quietly, to prepare for an inevitable, dramatic collapse. But this incredible journey, from trembling, luminous giant to eventual dying core, has only just commenced. And every story, every star, no matter how vast or spectacular its ending, always begins with the softest whisper. It all starts in the quiet arms of spiral galaxies, or nestled within the dense knots of stellar nurseries. These are vast, cold regions, immense clouds of molecular gas, mostly hydrogen, laced with the faintest traces of helium and other elements, stretching across dozens, even hundreds of light years. Our ship could drift for millennia through such a cloud, and you'd barely notice the subtle increase in interstellar dust. But under precisely the right, almost magical conditions, gravity, that unseen sculptor of the cosmos, begins its patient work. It starts to gently pull the gas inward, causing it to clump, to compress, to slowly, beautifully collapse. Within these sprawling, ethereal clouds, pockets begin to form, regions of ever-increasing density that we call prestellar cores. You might imagine them as cosmic cocoons, slowly gathering mass, and over time, if enough material coalesces, something truly remarkable begins to unfold. The temperature within these cores starts to rise, gradually at first, then with increasing fervor. As the gas contracts further, it heats up, atoms colliding with ever greater frequency, like tiny cosmic dancers speeding up their waltz. The pressure at the very center intensifies, building and building, until, eventually, that core becomes so incredibly hot and so extraordinarily dense that hydrogen atoms can no longer resist their mutual repulsion. They are forced together, overcoming the fundamental barrier, and begin to fuse, forming helium. In that singular, breathtaking moment, when the first fusion reaction ignites, that dense, hot protostar finally awakens, bursting into life as a true star. Isn't that just like space, to hide such power in such a quiet beginning? Yet, its destiny from that point onward, whether it becomes a small, long-lived, gentle dwarf, or a vast, short-lived, spectacular giant, hinges entirely on one crucial factor: the amount of initial mass it began with. If that collapsing cloud contained 10, 20, or even 100 times the mass of our own sun, the result is a massive star. And let me tell you, its life will be nothing short of intense, brief, and utterly breathtaking. You might feel a faint thrum of anticipation through the ship's structure, a subtle tremor as we consider such cosmic power. Once a massive star ignites, it enters its main sequence phase, the longest and most stable period of its existence, when hydrogen fusion powers its core. During this time, the outward pressure generated by all that furious fusion energy is perfectly balanced by the inward pull of gravity. This delicate equilibrium prevents the star from collapsing under its own weight, but also from expanding uncontrollably. It's a fragile piece, however. In a massive star, fusion occurs at incredibly high temperatures, burning through its hydrogen fuel at a truly furious pace. Our sun will last for billions of years, but a star with 10 times its mass may burn itself out in mere tens of millions. This astonishing speed of burning is a direct consequence of its immense mass. Heavier stars are not simply scaled-up versions of our own gentle sun. They are fundamentally more extreme, more ferocious. Their cores are hotter, their luminosity far greater, and their fusion rates dramatically higher. A star only 10 times as massive as the sun can be more than 10,000 times brighter. All that energy has to escape, and it does so by pushing outward against the star's outer layers, slowly inflating them over its relatively short lifespan. The gentle hum of the ship seems almost to echo this immense energy, a silent testament to the forces at play. As such a star ages, its core chemistry begins to subtly change, and new, more complex processes unfold, all driven by that same central, precarious balance between gravity and pressure. These colossal stars also don't exist in isolation. They tend to form in bustling clusters, surrounded by other young stars and active gas clouds. Their intense radiation and powerful stellar winds, streams of charged particles, can literally blow away nearby material, influencing the birth of other stars, sometimes even triggering new collapses in neighboring regions. They are cosmic architects, shaping their own neighborhoods. But this very brilliance, you see, is a double-edged sword. The same enormous energy that allows a massive star to shine so spectacularly also begins, paradoxically, to erode its own structure. Over time, that powerful radiation generates stellar winds strong enough to carry significant mass away from its surface, slowly stripping it bare. These powerful winds will eventually play a crucial role in shaping the very next phase of the star's magnificent, turbulent evolution. It's a slow, cosmic unraveling. As the hydrogen fuel in the core becomes depleted, that delicate equilibrium finally begins to break down. The core contracts further under the relentless pull of gravity, growing even hotter, while new fusion reactions ignite in surrounding shells of material. The star's outer layers respond dramatically by expanding, causing it to swell and shift in size, color, and internal structure. This marks the poignant end of its main sequence life and the beginning of something far more unstable. A turbulent transition into the later stages of stellar evolution, where maintaining balance becomes an increasingly desperate, losing battle as collapse looms large. Massive stars truly live fast and die young. Their breathtaking brilliance isn't a sign of endurance, but rather a testament to the unimaginable pressure, the scorching heat, and the furious speed of their internal processes. The more mass a star possesses, the more rapidly it consumes itself, burning through its precious fuel with an almost suicidal intensity. And in the ensuing stages of its life, that inherent speed becomes a kind of unstoppable unraveling, a relentless race toward instability that no force in the cosmos can halt. But before we get too lost in the dramatic end, it's worth remembering with quiet awe where every star's story truly begins. Every single star, no matter how vast it eventually becomes, begins its incredible journey as nothing more than a simple cloud in the quiet, often overlooked arms of spiral galaxies, or nestled deep within what we call stellar nurseries, those dense, fertile knots of nascent cosmic life. There exist vast regions filled with cold molecular gas, mostly hydrogen, of course, but always laced with the faintest traces of helium and slightly heavier elements. These are the fundamental ingredients. Our ship drifts now, experiencing the subtle changes in the void, a gentle sway that mirrors the universe's slow breathing. These initial clouds can be truly immense, stretching across dozens, even hundreds of light-years of space, quietly waiting. But under the precise, often serendipitous conditions, perhaps triggered by a passing shockwave from a supernova, or the gravity of a nearby spiral arm, that fundamental force, gravity, begins its patient, irresistible work. It starts to gently pull the gas inward, causing it to clump together, to compress, and to slowly, almost imperceptibly, begin its long collapse. Within these vast, diffuse clouds, pockets naturally form, regions that are just a little bit denser than their surroundings, which we call cores. And over cosmic eons, if enough mass steadily gathers within these nascent hearts, something truly remarkable starts to happen. The temperature within that core begins its slow, steady rise. As the gas continues to contract under gravity's persistent embrace, it heats up, the atoms within beginning to collide more and more frequently, their silent dance accelerating. And the pressure at the very center grows, building towards its inevitable destiny. Eventually, the core becomes so incredibly hot, so unbelievably dense, that those hydrogen atoms, usually so repulsed by each other, are finally forced to overcome their natural resistance and begin to fuse into helium, the very heart of it. A gentle ignition, not unlike the slow kindling of a cosmic flame. You feel a faint, almost imperceptible tremor through the deck plates beneath you, a soft vibration against your boots as you drift, perhaps slightly. At this moment, when that initial spark catches, when hydrogen atoms finally begin their slow, elegant dance of fusion, a protostar truly awakens. It becomes a star. But what kind of star? That, my friend, is where the universe gets wonderfully dramatic. It all hinges on a single, astonishing truth: how much material it managed to gather in its infancy. Imagine, if you will, the immense cosmic clouds from which these behemoths are born. If our nascent star had collected 10, 20, even 100 times the mass of our own familiar sun, then what emerges from the nebular dust will not be a modest, long-lived dwarf. Oh no, it will be a colossal, brilliant giant, destined for a life both breathtakingly intense and strikingly brief, a truly spectacular existence. As you gaze out the main viewport, the distant starlight paints shifting reflections on the console array, a quiet display of green and amber against the deep indigo of the cosmos. The hum of the life support system, always present, always reassuring, is the only sound truly breaking the profound silence. Once such a massive star ignites, it settles into what astronomers call the main sequence, a phase of relative stability. For a time, here, inside its fiery core, hydrogen fusion churns with astounding power, pushing outwards with just enough force to perfectly counter gravity's relentless inward pull. This delicate equilibrium, a cosmic balancing act, keeps the star from collapsing under its own weight, yet also prevents it from inflating uncontrollably into the void. It's a fragile truce, isn't it? A magnificent, precarious piece. You might need a moment to just float here, letting the vastness of it all wash over you. The recycled air feels cool and clean against your face. In these titans, the fusion process is an incredibly fiery affair, occurring at temperatures that would utterly defy comprehension. Their cores devour hydrogen fuel with a furious hunger, burning through their supply at an astonishing rate. While a gentle star, like our own sun, can patiently sustain its main sequence for billions of years, a star, just 10 times its mass, might blaze through its life in mere tens of millions. What a contrast, right? Such speed, such intensity, is a direct consequence of its immense mass. Heavier stars aren't just scaled-up versions of their smaller cousins. They are fundamentally more extreme. Their cores sizzle hotter, their light shines far, far brighter, and their fusion rates are dramatically, exponentially higher. It's truly incredible. A star, only 10 times as massive as the sun, can outshine it by more than 10,000 times. Think about that raw, unfiltered energy. It simply must escape, and it does so by gently pushing against the star's outer layers, slowly, incrementally, inflating them over eons. As these colossal stars mature, the very chemistry within their core begins to transform, new processes stirring to life, all still governed by that same central, fundamental balance between gravity's embrace and pressure's push. These giants often form in crowded stellar nurseries, surrounded by other young, energetic stars and active gas clouds. Their intense radiation and powerful stellar winds can sweep away nearby material, influencing the birth of new stars, or even triggering fresh collapses in neighboring regions. But this brilliance, this dazzling display, is a double-edged sword, a truly cosmic paradox. The very energy that allows a massive star to shine so spectacularly also begins to subtly erode its structure. Over time, that powerful radiation starts to drive relentless stellar winds, vast streams of energetic particles that continuously carry mass away from its surface. These winds, over millions of years, will ultimately sculpt the next dramatic phase of the star's evolution. As the hydrogen fuel in the core dwindles, the delicate equilibrium begins to falter, to waver. The core, sensing the change, starts to contract under gravity's renewed dominance, growing hotter and denser. Suddenly, fusion ignites anew in surrounding shells, like layers of an onion catching fire from within. The star's outer layers, responding to this internal upheaval, begin to swell, to expand outwards. The star itself starts to shift, altering its size, its color, its entire internal architecture. This, then, marks the end of its main sequence, the quiet, relatively stable chapter. It is the beginning of something far more unstable, a tumultuous transition into the later stages of stellar life, where that precious balance becomes increasingly difficult to maintain. The ominous shadow of collapse begins to loom large on the cosmic horizon. Why does the universe always do this to you, just when things seem so settled? Massive stars truly live fast and die young. Their spectacular brilliance is not a testament to endurance, but rather a stark indicator of the extreme pressure, the immense heat, and the incredible speed at which they burn through their lives. The more mass a star possesses, the more rapidly it consumes itself, relentlessly spending its precious fuel. And in the unfolding stages of its later life, that very speed transforms into a kind of irreversible unraveling, an accelerating race toward instability that no known force in the cosmos can possibly halt. You feel the ship itself seem to subtly shift, as if responding to the unseen cosmic currents around it. A soft murmur of the engines, a comforting drone. At the very heart of every star, a true crucible exists, a region where raw matter and immense energy are forged into something entirely new. During the longest initial phase of a star's existence, the primary reaction is, of course, the fusion of hydrogen into helium. In smaller, more sedate stars, like our Sun, this occurs through a relatively gentle process known as the proton-proton chain. But within the crushing, searing depths of more massive stars, the temperature and pressure are so astronomically high that they trigger a much faster, far more intricate reaction, the CNO cycle. It's named for the carbon, nitrogen, and oxygen nuclei that act as elegant catalysts, guiding the hydrogen nuclei to collide and combine, creating helium and unleashing truly gargantuan quantities of energy in the process. As these colossal stars age, that precious hydrogen in their core gradually depletes, spent in its fiery work. When this happens, the delicate balance between the outward pressure of fusion and the inward pull of gravity inevitably breaks down. The core, no longer supported, begins to contract under its own immense weight, becoming even hotter, even denser. This seismic shift triggers the next dramatic stage, helium fusion, where 3 helium nuclei are forcefully combined to form carbona process, known as the triple alpha reaction. From this point onward, the fusion process within the star evolves into a magnificent layered sequence. Each new element created in the core doesn't just sit there, it becomes the fuel for the very next round of reactions, like a cosmic nesting doll of fire. The core becomes surrounded by concentric shells of fusion, each one burning different elements at different depths, a breathtaking display of internal complexity. In the most massive of these stars, this chain of creation continues far beyond carbon. As the core contracts and heats even further, it begins to fuse carbon into oxygen, then oxygen into neon, neon into magnesium, and magnesium, finally, into silicon. And then, at last, the silicon fuses into iron. And that, my friend, is where the sequence, the grand cosmic alchemy, comes to an abrupt halt. Iron marks a hard, unforgiving limit. Unlike all the glorious fusion reactions that came before it, turning iron into heavier elements doesn't release energy. It consumes it. This fundamental truth means that once a massive star's core becomes choked with iron, it can no longer generate the outward pressure needed to resist the crushing, relentless force of gravity. Collapse becomes not just possible, but utterly inevitable. You feel a chill, perhaps not from the temperature of the recycled air, but from the sheer, raw finality of it all. This entire fusion process, from hydrogen to iron, unfolds with terrifying rapidity in a massive star's final stages. While hydrogen fusion might have gracefully lasted for millions of years, each successive phase becomes dramatically shorter. Helium burning might last 1,000,000 years. Carbon fusion, a mere 1,000. Silicon fusion, that can happen in just a few desperate days before the core gives way. It's as if the star burns faster and faster, the deeper it delves into its own structure, racing through the periodic table with an ever-increasing, desperate urgency. The internal layers become chaotic, turbulent, wildly unstable. Each shell of active fusion presses outwards with dwindling energy, even as that iron core inexorably tightens its grip, compressing under its own insurmountable weight. These frenetic fusion stages also directly dictate the star's ever-changing internal structure and its external appearance. Each reaction generates light and heat, contributing to the star's overall luminosity and driving powerful internal convection currents, creating a layered, glowing sphere with a seething, boiling atmosphere. Yet, from our distant vantage point, from the quiet sanctuary of our ship, these catastrophic internal changes are not always visible. A hypergiant, even in its terrifying final days, might look much the same to us as it did centuries ago. Isn't that just like space? So much happening beneath the serene surface. The faint thrum of the engine is almost a part of you now, a low vibration that resonates softly through the deck plating and into your very core, a gentle reminder of our tiny vessel's steadfast journey. Outside, bathed in the cool, recycled air of the cabin, the distant starlight paints shifting patterns across the console, a silent display of cosmic power. We were just observing one of those titanic furnaces, weren't we? It's astounding to think that deep within its heart, a nuclear maelstrom rages, a glorious, controlled chaos. The sheer energy born from that fusion doesn't just ignite a star, illuminating the immense dark. It intricately defines its entire being, its immense weight, its fiery brilliance, and the fleeting span of its existence. This profound connection, you see, is encapsulated in what we call the mass-luminosity relation. It whispers a fundamental truth. As a star's mass swells, its luminosity doesn't just increase proportionally, it skyrockets, expanding with breathtaking, exponential force. It's not a straight lineup, not a simple addition, but a dizzying curve, isn't it? Imagine a star, perhaps 10 times heavier than our own comfortable sun, yet blazing with 10,000 times its magnificent light. The consequences of such intensity are truly profound. The more radiant a star becomes, the more fervently it expels energy, and the more furiously it devours its precious fuel. You might even feel a subtle shift in our ship's gravity assist as we pass near a denser region, a tiny pull reflecting the cosmos's grand mechanics. This intense consumption is precisely why the most colossal stars burn so fleetingly. Their internal engines aren't merely robust, they're wildly, breathtakingly wasteful. A smaller, more unassuming star, much like our sun, can leisurely sip its hydrogen reserves, stretching them across billions of serene years. But these giants, they race through their fuel in a mere handful of million years. Their dazzling brilliance, you understand, isn't a promise of endurance, but a stark symptom of immense internal pressure and astonishing speed. It glows because it absolutely must, and in doing so, it paradoxically seals its own fate. Isn't that just like space, beautiful and utterly indifferent? If we could measure a star's life in breaths, these massive celestial beings would take deep, powerful inhalations, but only a precious few before their light fades. Their entire cosmic journey unfurls along a timeline that feels strangely condensed, almost brutally fast, especially when compared to the long, graceful arcs of smaller, gentler stars. Our own sun, with its single solar mass, might quietly grace the main sequence for 10 billion years, but double that to 10 solar masses, and suddenly its story shortens dramatically to 20 or 30 million years. Elevate that mass again, perhaps to 30 or 40 solar masses, and its entire magnificent life could be over in just a few million cycles. The most colossal stars we've ever glimpsed may blaze through their entire existence in less than a million years. To our human eyes, these still feel like impossibly vast stretches of time, don't they? But in the grand, silent clockwork of the cosmos, they are utterly fleeting, like a whispered secret in the roar of eternity. These magnificent entities form rapidly, shine with an almost defiant intensity, and, inevitably, die young. A familiar red supergiant, perhaps like Betelgeuse, has likely graced the cosmos for only a mere fraction of our sun's gentle age. And a hypergiant, something like Stevenson to 218, may have only lived for a few fleeting millions of years, already sensing the inevitable approach of its grand finale. From the moment of their fiery birth to the final, crushing embrace of collapse, these stars are caught in a relentless cosmic dance, fusing and radiating at an almost furious, breakneck pace. Their breathtaking brightness isn't a beacon of longevity. No, it's a palpable sign of immense internal pressure, an intrinsic urgency to forever hold the crushing grip of gravity at bay. You can almost feel that struggle, can't you? It's a silent battle playing out across light years. The quiet hum of our ship's life support systems seems infinitely stable by comparison, a comforting assurance against the universe's wild abandon. The profound reason these lifespans shrink so dramatically is deeply embedded in the very mechanics of how energy is forged and then expended within them. Fusion occurring deep within the core must generate an outward force potent enough to resist the star's colossal, crushing gravity. Yet, the more massive the star, the more incredibly powerful that gravitational pull becomes, demanding an even greater surge of energy to maintain its delicate, fiery equilibrium. Consequently, the rate of fusion accelerates, escalating with a terrifying efficiency. It's a non-linear climb, a steep, unforgiving curve. Hydrogen, the universe's most abundant fuel, is not converted into helium with a gentle, patient simmer. Oh no, instead, it's transformed in vast, thundering waves of heat and unimaginable pressure, each surge producing an intense, blinding luminosity and generating tremendous, outward-rushing stellar winds. The star shines with an almost unbearable brilliance, yet, in this magnificent display, it voraciously consumes its own vital essence. And this isn't merely a doubling of speed, it's an exponential explosion. A star twice as massive doesn't just burn twice as quickly. It can burn 10 or even 100 times faster. Imagine that for a moment. Why does the universe always do this to you? It's because the sheer output of fusion depends not only on the star's total mass, but, crucially, on the extreme temperatures and pressures at its very core, which surge dramatically with increasing mass. These infernal core conditions ignite even more energetic reactions, which in turn generate an even greater torrent of radiation. You can almost see the starlight reflecting off the distant nebulae, a silent testament to this fierce internal engine. That relentless radiation then exerts an outward push on the star's outer layers, compelling it to expand, almost to puff up, and to steadily shed its mass into the void. Simultaneously, this very same outward pressure, operating at the atomic level, relentlessly drives the fusion that powers the star. But as the star balloons larger and becomes ever more luminous, it paradoxically grows more fragile, more delicately balanced. Its own titanic energy output begins to subtly destabilize its magnificent envelope, a quiet unraveling you wouldn't notice unless you were truly looking. Radiation pressure in those outermost layers gradually overcomes gravity, and material, no longer firmly bound, begins its slow, inevitable drift away. What once began as an incredibly powerful engine of cosmic creation slowly, almost imperceptibly, starts to unravel. Even as its core continues its furious burn, the star's overall mass begins to diminish, carried off by relentless stellar winds and violent, sporadic outbursts. Over time, it relinquishes a significant portion of its original grandeur. Yet, in a strange cosmic paradox, it continues to burn hotter, fuse faster, and march steadily, gloriously, toward its own collapse. This is the profound, beautiful paradox of massive stars, the very immensity of their mass, which grants them such breathtaking brilliance, also inexorably guarantees their early, spectacular demise. They burn with an extraordinary, almost reckless power, sculpting galaxies with their light and scattering the cosmos with the elements forged within their fiery hearts. Yet, they simply cannot sustain themselves indefinitely. The more fuel they possess, the more rapidly it is consumed. And when that incredible fuel is finally exhausted, gravity, patient and absolute, takes its final, undeniable hold. Then, and only then, does the final dramatic transformation truly begin. For now, however, as we drift silently, they are still out there, those magnificent stars, still shining, still burning through their immense lives in a dazzling cascade of fusion reactions, pouring light and heat into the fathomless void. But deep within their blazing hearts, the cosmic timer is already running down, a silent countdown. And even as you watch, the intricate layers of the star are subtly shifting, reconfiguring themselves, preparing for the next, inevitable phase of their colossal journey. You might even feel a subtle temperature change in the cabin, a reminder of the vast, shifting energies out there. As a massive star ages, that once tenacious balance it held so fiercely begins to fray, like an ancient tapestry slowly coming undone. Its core, now burning with even greater urgency than ever before, is drawing its colossal mass ever inward, while its once stable atmosphere gently, almost invisibly, starts to drift away. This process begins with an understated grace, almost imperceptibly, as powerful stellar winds begin to rise from its incandescent surface. These aren't just gentle breezes like we know on Earth. Oh no. They are relentless, potent streams of fundamental particles, atoms and ions, literally propelled outward by the sheer, unbridled intensity of the star's radiation. Driven by light itself, they surge through the emptiness of space at breathtaking velocities, hundreds or even thousands of kilometers every second. That's faster than anything you can truly imagine. Over the vast stretches of cosmic time, these unseen currents carry away truly staggering amounts of stellar material, shaping the very fabric of the star from the outside in. Nothing to worry about, probably. This steady, persistent exodus of mass can dramatically alter the entire evolutionary trajectory of a star, bending its destiny to a different path. For the most titanic red supergiants and hypergiants, this rate of mass loss accelerates dramatically in their final twilight stages. A star like Vi Canis Majoris, for instance, might shed as much as 1 Earth mass every single year. Just imagine that scale for a moment. Over the course of its long, dying phase, such a titan can relinquish more than half of its total original mass, all that gas and plasma that once helped it valiantly resist gravitational collapse, now silently drifting outward into the vast, waiting interstellar medium. These powerful stellar winds don't merely thin the star's outer layers. They actively reshape its entire atmosphere, sculpting it into immense glowing halos and delicate arc-like structures of drifting material. You might see them shimmering softly in the infrared, or perhaps catch their faint ethereal whispers in radio light, a ghost of what once was. It's a testament to the star's internal struggle, its last grand gesture. This isn't just loss. It's a profound transformation, an elegant, destructive dance that continues to unfurl across the void. And with that, the stage is set for the next chapter. And you feel a faint, almost imperceptible tremor running through the deck plates beneath your feet, a subtle reminder that the universe, even in its most majestic forms, isn't always smooth. Out there, the colossal outer layers of a dying star begin to undulate, sending vast waves and soft pulses rippling across its immense, fiery surface. These deep, cosmic breaths aren't random. They're the star's internal dialogue, whispers of shifting energy flows, enormous convection currents, or even tiny, partial collapses deep within its outer fusion shells. As the pressure builds, you can almost imagine it expanding slightly, then gently contracting again, a slow, patient heartbeat that spans not seconds or minutes, but months, even years. Isn't that just like space? Always doing things on its own grand timeline. With each of these grand pulsations, the star's ethereal outer atmosphere is nudged outward, a delicate dance against the pull of gravity. Sometimes it's pushed just far enough that gravity can no longer reclaim it, and a ghostly wisp of gas floats away into the surrounding void. This gentle, episodic mass loss is a critical part of its transformation. You might even glimpse faint, shimmering arcs if the light is right, like silent echoes of a stellar exhalation. Deep within those outer layers, enormous bubbles of superheated gas are constantly rising, carrying their vast stores of energy towards the surface, only to cool and gracefully sink again. These convection currents are truly immense, spanning entire percentages of the star's unimaginable diameter, creating a ceaseless, rolling churn throughout its colossal envelope. Within the heart of such a red hypergiant, this deep internal convection can grow truly turbulent. You watch, perhaps, as the star's surface appears to break in places, manifesting as fleeting, impossibly bright spots or cooler, darker patches. It's no longer a smooth, static sphere in the traditional sense. It boils with an almost silent fury, a slow cosmic simmer on a scale beyond human comprehension. This boiling is a driver of further instability, each convection plume a brief flare of local brightness, subtly altering the pressure and, sometimes, triggering the graceful ejection of more material. These outbursts, though gentle, from our distant perspective, can form visible, ethereal structures, arcs, loops, or faint, nebulous shells that drift silently away from the star, becoming ghost images against the darkness. These expelled structures, often invisible to your eyes in standard light, are beautifully revealed by specialized instruments, captured as shimmering infrared arcs or delicate bow shocks, where the star's departing breath gently collides with the interstellar medium. With each whisper of mass it releases, the star grows fractionally lighter, yet not necessarily more stable. The shedding is uneven, a testament to the extraordinary pressures still at play within its core. Its stretched, fragile surface is constantly tugged outward by the sheer force of radiation and inward by gravity's relentless embrace, never quite finding equilibrium. It truly is a slow unraveling, isn't it? The star's immense size may even continue to swell as its outer envelope begins to softly evaporate into the cosmic ocean. Yet, this gentle surrender of mass is far from an ending. It is a profound transformation. The material being shed, those shimmering gases and dust, will not simply vanish. Oh no, it will gracefully drift and become an intrinsic part of the galaxy once more, a cosmic inheritance. This stellar breath will feed the birth of new stars, coalesce into nascent clouds, sculpt intricate dust lanes, and lay the foundations for future planetary systems. Even as this hypergiant softly loosens its grip, it is generously giving something fundamental back to the grand cosmos. As more mass drifts away, the star's outermost layers grow increasingly delicate, more fragile, and vastly more extended, blurring the very definition of what we once called a surface. What we might have once thought of as a solid edge no longer exists in any simple way. Instead, the outer atmosphere now forms a vast, diffuse envelope of glowing gas and plasma, subtly spreading outward into the immense darkness. Imagine, if you will, a star like Stephenson to 218, where this envelope could stretch across hundreds of millions of kilometers without any distinct boundary, just a slow, gradual fading from dense inner layers to almost imperceptible wisps at its furthest reaches. It's not a solid shell you're looking at, but a continuous gradient, always in motion, always shifting. These extended atmospheres, so vast and tenuous, are incredibly unstable. Shaped by convection, radiation, and turbulence, they softly fluctuate through time. Regions within this ethereal atmosphere might gently brighten or dim, expand or contract, or even subtly peel away entirely, like layers of an otherworldly onion. Deep internal pressure waves, born from the ever-changing fusion rates within the star's core, ripple outward, softly disturbing the delicate equilibrium between gravity's pull and the outward forces. Because this material is so incredibly loosely bound, even the smallest of disturbances can instigate massive, graceful ejections. The result, you observe, is an atmosphere that subtly flickers and flows, like a dreamlike storm system stretched across the scale of an entire solar system, a mesmerizing slow-motion ballet of cosmic forces. Within these swirling diaphanous conditions, new structures quietly begin to take shape around the star. As gas is gently expelled and drifts into the interstellar medium, it slowly cools and condenses, forming what we call circumstellar envelopes, loosely bound regions of gas and dust that gradually enshroud the star like a soft, luminous veil. These fragile envelopes can stretch far beyond the visible glow of the star itself, sometimes reaching many thousands of times its own immense radius. They aren't truly a part of the star in the traditional sense, but neither are they truly separate. They occupy a fascinating middle ground, material that once belonged to the star now suspended in a slow, silent orbit around it, glowing with a soft, inviting warmth only truly visible in the infrared spectrum. The very composition of these ethereal envelopes whispers stories of creation. Some, we find, are remarkably rich in oxygen, while others contain vast amounts of carbon. You might imagine tiny, iridescent crystals of silicate or graphite formed as the superheated gases from the star cool and coalesce, now drifting aimlessly through space. Still others harbor more complex molecules, including water, carbon monoxide, and even the simplest organic compounds, all suspended and slowly swirling in the vast outer reaches of a dying star's influence. These precious materials, once forged by immense fusion and heat, are now gently returning to the cosmos, where they may one day become the building blocks of new planets, emerging moons, or perhaps even other stars. When our sophisticated instruments, like infrared or radio telescopes, turn their gaze upon these envelopes, we often perceive them as delicate clouds, graceful arcs, or shimmering shells, faint, ghostly structures that encircle the central star, like ghostly structures that encircle spreading across a vast cosmic pond, comet pond, peeping, and was so, kipsoid, when his pruity was so yet to do go by side, I be like I did that of yet that by the I be you to with a come to where I you did him wo I'm past we without a fifth by fat to the fifth by we Sometimes, these arcs appear uneven, beautifully sculpted by previous, ancient eruptions, or by the gentle gravitational embrace of nearby stars. In binary systems, the soft stellar winds from one companion may gently push against the other's envelope, shaping it into elegant spirals, or sweeping it into long, flowing tails. These intricate formations are often completely invisible in ordinary light, but with the right instruments, they reveal a profound, mesmerizing record of the star's final lingering centuries. Over immense stretches of time, these circumstellar structures will slowly evolve into full-fledged nebulae, should the star's core eventually collapse, sending out a powerful, albeit brief, shockwave. The expelled material will be propelled even farther outward, beginning to glow brilliantly in response to the intense heat and radiation from that final, dramatic explosion. This, you realize, is the breathtaking origin of many of the most beautiful nebulae we admire today, formed from the extended, glowing envelopes of dying stars, now exquisitely lit from within by the aftermath of collapse. But even before that ultimate moment, the delicate formation of these structures is already well underway. The entire process is both incredibly chaotic and exquisitely elegant. A star, approaching its cosmic twilight, gently sheds itself layer by layer, not all at once. The material that departs from its embrace is not waste, it is. Drifting gently through the cosmic currents, we find ourselves surrounded by a silent symphony, a grand legacy whispered from the heart of every distant star. Imagine, if you will, the delicate fingerprints of creation carried on every photon, the ancient warmth of stellar cores, the very elements forged in unimaginable fiery furnaces, all now reaching us across the vast, cool void. And out here, amidst the profound darkness, These softly luminous, swirling clouds we observe aren't just pretty nebulae. They are the graceful, slow farewell of a colossal star, a giant reaching the twilight of its existence. While the star's outermost layers, now stretched incredibly thin and faint, might seem to vanish into invisibility, our clever tools aboard this vessel, reading the subtle shifts in the console lights, allow us to perceive what was once hidden. We're not seeing them directly, of course. We're reading the light itself. As the star pours its radiance into the emptiness, that light must first pass through its own sprawling atmosphere, like a whispered secret passing through a vast ethereal veil. And in doing so, it leaves behind an unmistakable signature, a complex, almost poetic fingerprint, etched in the wavelengths story of its elements, its movements, its very structure. This is the quiet magic of stellar spectroscopy, isn't it? Such an elegant way to listen to the universe. By carefully splitting that starlight into its individual chromatic components, much like a prism separating a single beam into a rainbow, our instruments can detect the presence of specific atoms and molecules, the incredible speeds of gas flowing across light years, and even discern the density and temperature of those incredibly distant layers. You see, each individual element has its own unique hunger for light, absorbing it at very precise, telltale wavelengths. When that element exists within the star's expansive atmosphere, it carves out these subtle absorption lines, narrow, almost imperceptible gaps within the otherwise continuous spectrum of light, where energy has been quietly claimed. The strength of these lines, their unique shape, even their exact position, reveals so much. A line that appears a little broader, for instance, might be whispering tales of swift, turbulent motion within the gas, perhaps a chaotic dance of stellar winds. And if a line shifts towards the red end of the spectrum, it's a clear sign that gas is flowing outward, moving away from the star, a gentle exhalation into the cosmos. Conversely, a shift towards the blue suggests material falling inward, or perhaps cycling through those vast, churning convective layers, like slow, celestial eddies. By meticulously analyzing these intricate features, our astronomers, with their patient dedication, can map the incredible dynamics within a hypergiant's outer envelope in astonishing detail, even from thousands of light years away. Isn't that just like space, hiding its grandest secrets in the smallest of details? For celestial titans like Vicanus Majoris, or the familiar glow of Betelgeuse, and the colossal Ui Scuti, these spectral observations have unveiled rhythmic pulsation cycles, dramatic zones where vast amounts of mass are being ejected, and even surprisingly complex molecular chemistry thriving in their upper atmospheres. Imagine molecules like water vapor, silicon monoxide, and carbon monoxide, substances you might find within these fiery outer atmospheres, defying what you might expect, given the immense temperatures and the incredibly low of la drew is it half creature to the prayer of ko per his so give bit of like up would you back if I put it to do up to bed I asked if to you go by you to you other you saw you go so I would take you though I click I saw you but in certain cooler, sheltered pockets of these giants, these molecules manage to cling to existence just long enough to emit a faint light of their own, often glowing in the infrared or radio wavelengths. Observing that subtle glow offers scientists an unparalleled window into the star's slow, magnificent unraveling, and, crucially, into the ultimate fate of all the material it so generously releases into the universe. These profound studies, you see, don't just illuminate the star itself. They also reveal how the fading giant interacts with the vast, empty space surrounding it. As its colossal mass drifts outward, it doesn't simply vanish into nothingness. Oh no, it inevitably collides with the interstellar medium, that incredibly diffuse tapestry of gas and dust that weaves its way throughout our galaxy, leaving an indelible mark. In some breathtaking instances, this creates colossal shock fronts, immense, invisible boundaries where the star's relentless winds pile up against the resisting interstellar gas, heating it and compressing it into spectacular arcs or delicate, luminous filaments. These magnificent structures, often completely unseen in the visible light our eyes perceive, glow with startling brilliance in the infrared or ultraviolet, allowing our instruments to trace the star's long-term influence across truly astronomical influence, acrotonomical intectinets cannot, in a pew to ascend in a senesokua of it, and in it a plus a within way per you did I give pre I would to pull what I put up with if I interview to I will yep I perved me that of the two by me the cup up I good poet would blue these thinkers but sky bears to the star's intense radiation also profoundly affects the nearby space, much like a cosmic beacon. Its powerful ultraviolet light can ionize surrounding hydrogen, creating faint, glowing bubbles of energized gas. These high regions, named for that ionized hydrogen, are commonly observed around energetic young stars, but even ancient dying giants can produce similar ethereal effects as they approach their end. Even those incredibly low-density envelopes, barely clinging to the star, can reflect, scatter, or reshape the light emanating from the core, creating a vast, glowing halo that extends far, far beyond its original edges. These effects might appear subtle to our human perception, yet they represent an incredibly powerful force. A single hypergiant, even in its dying throes, possesses the power to reshape its entire surroundings across light years of space, a cosmic sculptor in its final act. In regions where other stars are currently forming, the influence can be even more profound, a ripple effect through creation. The very shockwaves and winds unleashed from a dying giant possess the capacity to compress nearby clouds of gas and dust, triggering the gravitational collapse that births entirely new stars. In this extraordinary way, the spectacular death of one star becomes the vital catalyst for the birth of many others. This process of triggered star formation, a beautiful example of cosmic recycling, is believed to play a significant role in shaping the structure of stellar nurseries and the grand evolution of galaxies themselves. It is a fundamental part of the cosmic cycle, that constant, majestic exchange of matter and energy from one generation of stars to the next, eternally renewing the universe. So, even as the star's atmosphere thins and becomes increasingly unstable, its profound reach, paradoxically, grows wider. The mighty gravity that once held its immense mass so firmly in place has finally loosened its grip, its strength waning. The colossal energy that once pushed outward now drives material far beyond its former, once-defined edges. In this quiet, awe-inspiring unraveling, the star transforms from merely a dying object into something far grander, a shaper of space, a sculptor of the interstellar medium, and a profound bridge between the past and the vibrant future of the cosmos. As we continue our slow drift, observing this cosmic drama, let's consider the inner world of such a massive star at the very end of its long, burning life. Inside, it becomes layered like a celestial onion, each skin a different element. Hydrogen fusion, its first source of light and energy, has long since moved to the outer layers, replaced at the core by concentric shells of helium, then carbon, oxygen, and progressively heavier elements, each igniting briefly before succumbing to the crushing weight and giving way to the next. At its very center, the star's iron core contracts relentlessly under its own immense weight, becoming ever hotter, ever denser with each passing moment, a ticking clock of cosmic proportions. Eventually, the core begins to fuse silicon, a final, desperate act in the incredibly long chain of nuclear reactions. And then, quite abruptly, the process stops. Not just slows, mind you, but stops entirely. Because, unlike the fusion of lighter elements, the act of forcing iron nuclei together to fuse actually absorbs energy rather than releasing it. It simply takes more energy to accomplish the fusion than the reaction itself can provide. For a star, this is an utterly catastrophic change, isn't it? A fundamental betrayal of its very purpose. The newly formed iron core grows rapidly, fed by the collapsing layers above it, supported only by the intense, almost magical pressure exerted by degenerate electrons. It's the same quantum pressure that bravely holds up white dwarfs against total collapse, a truly immense force. But even that pressure has its limits. There's a cosmic threshold. As the core approaches roughly 1.44 times the mass of our own sun, a critical boundary known as the Chandrasekhar limit, the delicate balance shatters completely. There is no new fuel left to ignite, no outward force mighty enough to resist the overwhelming pull of gravity. The star, in its long, magnificent life, has unwittingly constructed its own undoing. It has forged a core it can no longer possibly support. In that singular, terrifying moment, gravity, always patient, always waiting, finally, completely takes over. With no more fusion pressure to oppose its relentless grip, the iron core begins to collapse inward at an almost unimaginable speed, nearly a quarter the speed of light. In less than a single second, the core shrinks from the size of a planet, a colossal world, down to the improbable dimensions of a small city. The electrons that once provided that crucial outward pressure are violently forced into atomic nuclei, combining with protons to form neutrons. This astonishing process, fittingly called electron capture, unleashes an instantaneous, staggering burst of neutrinos, those tiny, ghost-like particles that escape the core in vast, silent torrents, speeding away into the universe as if nothing had ever stood in their path. You're nestled comfortably within the soft hum of the ship, a faint, rhythmic vibration seeping through the cool deck plates beneath you. Outside, the endless canvas of the void stretches, speckled with distant, unblinking eyes of stars. One particular star, a magnificent red giant you've been observing, seems to shimmer with a familiar glow, yet deep within its heart, an unimaginable drama is unfolding. We're watching the very fabric of its existence begin to fray, a silent, internal catastrophe driven by the relentless grip of gravity. Can you feel the subtle sway of the ship, almost imperceptible, as we drift closer to this cosmic theater? It's a gentle dance with the cosmos. Inside that colossal star, a quiet, almost imperceptible collapse has begun. It's not a gentle fading, but a profound gravitational implosion where matter is being crushed inward, piling into an intensely dense neutron core. This sudden, violent stiffening creates a ripple, an outward tremor that is the first whisper of what will soon become a spectacular supernova. Yet, from our vantage point, the star still appears whole, its outer layers entirely unaware of the frantic, silent transformation consuming its heart. The light from its final moments hasn't even had a chance to escape. Nothing to worry about, probably. The pressures and densities within that collapsing core are utterly mind-boggling, truly beyond human comprehension. In less than a blink of an eye, the core reaches a density greater than an atomic nucleus itself. Imagine 10 trillion kilograms packed into every cubic centimeter. At this extreme scale, atoms as we know them simply cease to exist. Matter transforms into a swirling, supercompressed sea of neutrons pushed to the very edge of physical law. It makes you wonder, doesn't it, what ultimate forms matter can take. Now, here's where destiny hangs in the balance. If that collapsing core holds just a tiny bit too much mass, even the incredible resistance of those neutrons will fail, and the core will continue its desperate fall, creating a new, terrifying entity, a black hole. But if the mass remains just under that critical limit, a new celestial marvel is born, a neutron star. Imagine, if you can, a single teaspoon of this new material weighing more than Earth's Mount Everest. Truly astonishing. While this incredible shrinking act is happening at the core, the outer layers of the star are finally beginning to respond, pulled relentlessly inward by the escalating gravity. But then, a moment of profound cosmic defiance, the core's sudden rebound, fueled by the formation of the neutron core and a torrent of escaping neutrinos, begins to push back. A powerful shock wave starts to build, moving outwards. For a fleeting instant, the star's interior is pure, beautiful chaos. This collapse phase is incredibly brief, a mere handful of milliseconds. But what unfolds in that infinitesimal window will seal the star's ultimate fate. Will it erupt in a glorious explosion, silently implode into oblivion, or vanish without a trace? It's a moment where time and pressure fold in on themselves. The star, which has diligently burned for millions of years, now races through its final desperate breath, its center a crucible of exotic physics. And yet, from here, through the soft glow of our console lights, nothing appears to have changed. The star's surface still radiates with that same comforting red glow. Its gentle winds still drift softly outward, just as they have for ages. But deep, deep within, the collapse is a relentless force, already in motion, and there isn't a power in the universe that can halt its inexorable progress. As the star's iron core plummets inward, it accelerates, driven by gravity's immense, unforgiving pull. All resistance is gone now. No more fusion pressure, no internal energy to push back against the inevitable. In the final, infinitesimal fraction of a second, the core undergoes a catastrophic implosion. The matter inside freefalls, gaining incredible velocity, shrinking from thousands of kilometers across to mere tens. Electrons are forcibly merged into protons, and protons are crushed into neutrons. At this utterly extreme point, the enigmatic laws of quantum physics take over, and these newly formed neutrons resist further compression with a powerful force known as neutron degeneracy pressure. It's the universe's last desperate defense before a black hole takes hold. When this imploding matter finally reaches nuclear density, the collapse slams to a halt. The infalling material smashes into the newly formed, incredibly solid core, a dense sphere of neutrons packed tighter than anything else in the known universe, and the result is an extraordinary rebound. This sudden, violent stop generates an immense pressure wave that races outward through the star's collapsing layers. This is what's known as the core bounce, the precise moment the star's interior literally punches back against its own demise. Isn't that just like space, always full of surprises? However, this bounce alone isn't quite enough to trigger the full supernova. Most of its energy is quickly absorbed by the surrounding material, causing the nascent shockwave to stall, to almost give up. But the missing ingredient, the crucial cosmic push, is already on its way. A silent flood of neutrinos during the core collapse. An unimaginable torrent of these nearly massless particles is produced, trillions upon trillions, each carrying away a tiny, almost imperceptible fraction of energy. Though these elusive neutrinos rarely interact with ordinary matter, the density within the star's core is so astonishingly high that a small percentage do collide with atomic nuclei in the outer layers. This subtle transfer of energy is just what the universe ordered. It reinvigorates the stalled shockwave, giving it a renewed, powerful thrust outward. In a mere fraction of a second, the star's inner turmoil transforms from a quiet, desperate collapse into a magnificent, outward explosion. This neutrino-driven mechanism is one of the most critical, yet least visible, steps in the dramatic life of a dying star. The sheer number of neutrinos involved is truly staggering. A typical core collapse event releases more than 10 to the power of 58 of them. That's a 1, followed by 58 zeros. Almost none of them ever reach our distant ship, or Earth for that matter, but a precious few do. And in rare moments, our detectors catch them. This is how we first understood the collapse of supernova 1987A, not from its light, but from a handful of ghost-like particles that arrived hours before the explosion became visible. Together, the core bounce and that flood of neutrinos generate the monumental shockwave that begins to tear the star apart from the inside out. As this immense wave surges outward, it superheats the overlying layers, vaporizing elements, disintegrating atoms, and blasting the material into the vastness of space. The shockwave travels at an extraordinary speed, ripping through each shell of the star's structure. What took millions of years to meticulously build is now being unmade in mere seconds. The star is entering its most dramatic moment, a brilliant final flash that will echo across the cosmos for centuries. And yet, even as we witness it, most of this profound story remains entirely invisible to our eyes. The neutrinos don't glow. The core bounce makes no sound. Even the initial stages of that shockwave are hidden deep within the star's turbulent atmosphere. From outside, the familiar red glow continues, just for a little while longer, a tranquil mask over an internal inferno. But inside, the explosion has truly begun. The star's very structure is coming apart, being unraveled thread by thread. This collapse is rapidly evolving into an event that will utterly reshape the surrounding space and leave behind a cosmic remnant unlike anything else in the galaxy. This entire process, from the core's implosion to the dramatic bounce to the final outward shockwave, happens in less than a second. It's one of the most violent and consequential transformations in the universe, and yet it unfolds in perfect, profound silence. The light from this internal cataclysm hasn't yet reached the star's surface. The star itself hasn't vanished, not yet, but deep within its heart, its final, earth-shattering act is now irrevocably underway. In these fleeting milliseconds, before a supernova becomes fully visible, the internal structure of that distant star reaches its absolute, most critical point, a cosmic tightrope walk between existence and obliteration. You might need a moment to just float here, suspended in quiet awe. You're watching as the universe performs an act of colossal alchemy, deep within the heart of what was once a star. A fresh, powerful shockwave, invigorated by a sudden rush of neutrinos, is tearing its way outward. Behind it, a brand new neutron star, barely a flicker old, spins with dizzying speed, radiating an almost primal gravitational energy that even here you can almost feel as a subtle shift in the ship's orientation. Ahead of this expanding force, the star's own material, still collapsing, is getting sliced and diced, layer by dense layer. Each region, with its unique characteristics, is superheated, triggering brief, furious bursts of fusion. It's an unraveling, an obliterating of every boundary that held this star together for eons. Imagine, if you will, gamma rays erupting like silent fireworks, atomic nuclei being torn apart and then instantly reassembled. New elements are born in this furious, fleeting instant. Iron, once the stable anchor, is shattered, while lighter nuclei are slammed together by the intense heat, forging into nickel, cobalt, and a host of other heavy metals. This incredible process, known as explosive nucleosynthesis, brings these elements into being in less time than a single beat of your own heart. They are destined to scatter across the galaxy, the building blocks for, well, for everything. The physics at play here defies our everyday understanding. Forces stronger than any machine you could ever conceive are operating across distances measured in kilometers, unfolding in mere fractions of a millisecond. Truly, this is the universe at its most dramatic. And then, just like that, the shock wave reaches the star's outer edge. You feel a faint tremor through the hull, a deep, resonant vibration that might just be the ship's engines, or perhaps a sympathetic hum with the cosmic event unfolding before you. In that very instant, the star's light subtly, then profoundly, changes. After millions of years of steady, predictable fusion, and months of quiet, internal collapse, the star begins to brighten. The long-anticipated, visible supernova has finally arrived. A blinding flash of radiation bursts outward, momentarily washing out the softer glow of your console lights, followed by a sustained increase in brilliance that could easily last for days, or even weeks. It's an astonishing display. Yet, for all its spectacular brilliance, what you're truly witnessing now is already the aftermath, a cosmic echo of the actual cause. The deep, fundamental transformation, the moment the star truly remade itself, has already occurred, hidden from your direct view. It's a bit like watching a distant fireworks show, knowing the true explosion happened long before the sound reaches you. You ponder this as your recycled air hums softly around you. At the very center of this collapse, time itself begins to behave ... differently. As the core contracts, its gravity intensifies beyond anything comprehensible, warping the fabric of space-time around it in ways that are both elegant and unsettling. This profound effect, a cosmic ballet predicted by general relativity, means that time actually slows down near objects with such extreme gravity. To your distant vantage point, the collapse seems to unfold quite normally, a grand, if distant, spectacle. But imagine, for a particle or even a photon trapped deep within that incredible gravitational well, time ticks so much more slowly. If that core were to become a black hole, this time dilation would become utterly dramatic. In theory, the final moments of such a collapse could stretch towards infinity, utterly frozen at the very edge of the event horizon. Why does the universe always do this to you? It adds such layers of complexity to simple observation. Even before reaching that ultimate threshold, time dilation plays a measurable, subtle role. Consider the neutrinos we spoke of earlier, those ghostly particles that escape the collapsing core. They arrive at your ship, at Earth, before the light from the visible explosion does. And it's not just because they surge ahead of the shockwave, but also because the light itself is delayed, struggling through layers of dense plasma, and, crucially, by the very effects of this extreme gravity. The deeper you gaze into the star's heart, the more slowly time passes compared to its outer regions, or to your distant observation deck. This means a star's death isn't one singular moment, but many, stacked and curved by the very warping of space and time. This peculiar slowing of time, while adding a profound layer of mystery, doesn't halt the collapse itself. It simply means that you are observing an event through a truly distorted lens. When you look at a supernova from afar, like this, you're only truly seeing the bright, outer echo of something far more fundamental that occurred deep within a space-time twisted almost beyond recognition. We can model the physics, measure the incoming light, even capture a few of those elusive neutrinos. But the actual collapse, that pure, internal moment when a star utterly transforms, remains forever hidden from us, cloaked by vast distance, immense gravity, and the strange, fluid nature of time itself. And so, just before the brilliant explosion fully appears to you, the core, in its original state, is already gone. The final, crushing collapse has occurred. The powerful rebound has passed. The initial wave is already surging outwards through the stellar material, carrying the seeds of new worlds. And time, for a hushed moment, has bent in quiet reverence around that dying star. You feel a subtle shift in the ship's gentle forward momentum, a barely perceptible drift, as if the very void is holding its breath. When that shockwave finally breaks through the star's surface, tearing it asunder, the transformation is truly complete. What began as a quiet, relentless, gravitational collapse now explodes into a supernova, a cosmic event so staggeringly powerful that for a fleeting time, a single star can actually outshine an entire galaxy. Imagine that scale for a moment. Its light reaches across millions of light years, crossing the vast, silent void. To distant observers like yourself, it appears suddenly a dramatic new point of brilliance in the sky, where moments ago there was only the familiar darkness. But remember, this blinding brightness isn't emanating from the core itself. No, it comes from those outer layers, now violently ripped apart and hurled into space at speeds of tens of thousands of kilometers per second. This, my friend, is a core collapse supernova. This is the explosive, grand finale of a truly massive star, marking the sudden, catastrophic release of energy that was once bound in the slow, steady process of fusion. Now, in a mere fraction of a second, it's all liberated. The explosion itself isn't just one single flash, but a complex, beautiful unfolding. There's an initial burst of light, the shock breakout, followed by a much longer, lingering glow. This glow is first powered by the sheer kinetic energy of the blast. Then later, almost intimately, by the slow dance of radioactive decay. The very elements created in those final, furious milliseconds, like nickel-56, begin to decay into cobalt and iron, releasing gamma rays that heat the expanding gas, prolonging the star's final, magnificent illumination. The shockwave, now a roaring cosmic tempest, carries with it an immense amount of matter and momentum, smashing through each remaining shell of the star, vaporizing everything in its path. The once stable, distinct layers of hydrogen, helium, carbon, and oxygen, the very building blocks of the star, are torn apart, reshaped, and flung outward into the profound vacuum. This expanding cloud of stellar debris is unbelievably hot, incredibly dense, and glows with an inner fire. As it slowly cools across unimaginable stretches of time, it will begin to reveal the rich chemical legacy of the star. These are the ashes of fusion, now drifting freely through the interstellar medium. And here's a thought, just between you and me. As your ship's internal temperature stabilizes to a comfortable equilibrium, and you gaze out at the vastness, every single atom of calcium in your bones, every bit of iron coursing through your blood, was once forged in such a cataclysmic moment, born in the death throes of a giant star countless eons ago. Isn't that just like space, to remind us of our tiny, yet utterly cosmic origins? It's a humbling, awe-inspiring connection, linking your very being to these grand, violent events unfolding before your eyes. You might need a moment to just float here, letting that sink in. But alongside this blinding explosion, an invisible storm is brewing, a silent maelstrom of cosmic particles. In the fleeting seconds after the core's collapse, the star emits an incredible flood of neutrinos, more than 100 times the number of atoms in the entire observable universe. Think about that for a moment. These ghostly neutrinos, though almost massless, are the true energy carriers, whisking away most of the colossal power released by the event. Only a tiny fraction of them ever escape detection, but those precious few provide scientists with the earliest, most intimate signs that a supernova has occurred, long before the light from this magnificent explosion reaches us, before the expanding gas truly begins to glow with its full, radiant glory. A tiny, almost imperceptible signature appears in specialized underground detectors back on Earth. It's a flicker, a whisper from the deep cosmos, telling us something profound has just happened. Your own ship's subtle sensor array, if tuned just right, might even register a faint, almost statistical anomaly in the background radiation, a ghostly echo of that immense, invisible torrent. The universe, in its own enigmatic way, always sends its messengers, ... The final ethereal whisper of a star's passing. As you drift closer, the faint shimmer on your primary view screen resolves into a truly immense phenomenon, a colossal shockwave, steadily unfurling through the quiet emptiness of space. It's like watching an invisible hand sweep through a cosmic garden, gathering up stray specks of interstellar dust and gas, gently sculpting them into vast, glowing shells and intricate, delicate filaments. These cosmic structures, warmed to incandescence by the propagating energy, emit a soft, otherworldly glow in wavelengths far beyond what our eyes can see. Yet your ship's sensors register their presence, translating them into faint, swirling lights across your console. Isn't that just like space? Isn't that, but be it to, isn't be so, to it to who it to it to so in a bet to it so and we was it to you to get you with for work I look at you like ka you pipaya for I but it down I had to stuck I get you that's typical put the god up fuga up to and with the suckies arc like would if I don't get it to be. Even in destruction, there's always a breathtaking artistry. These vast, expanding halos, sometimes stretching for hundreds of light years, persist for millennia, a slow, majestic ballet in the void. Occasionally, they become visible to us, blossoming into what we call supernova remnants, intricate tapestries of gas and stellar dust that continue to hum with residual energy long after their parent star has vanished from sight. You can almost feel the residual warmth, a subtle rise in the ship's ambient temperature, perhaps from the distant radiation, or just your imagination. The ship itself seems to breathe with a soft, steady hum echoing the deep rhythms of the universe. As this spectacular debris cloud continues its slow, outward journey, it gradually begins to cool, its initial blinding brilliance mellowing. The vivid, visible light that once announced its dramatic end gently recedes, replaced by the more subtle, lingering emanations of infrared and radio waves. Yet, even in this gradual fade, a treasure trove of information remains. Delicate threads of data woven into the expanding fabric of the universe itself. These are the precious clues that interstellar explorers like us, and the patient astronomers back home, meticulously gather to piece together the cosmic drama that unfolded. The speed at which the material was expelled, its precise chemical makeup, its current temperature, each detail contributes to the unfolding narrative. And how fascinating it is to consider that no two of these stellar goodbyes are ever truly identical, are they? Some, you see, quietly birth a neutron star, while others, far more dramatically, succumb to a final, inescapable collapse, giving way to the profound mystery of a black hole. Some explode with a graceful, almost perfect symmetry, while others erupt with an almost playful, lopsided force, sending jets of material hurtling off in unpredictable arcs, painting abstract strokes across the cosmic canvas. What truly endures isn't an ending, but a profound transformation. The magnificent star itself may be gone, yes, but its very essence is now scattered far and wide. Its vast energies have been meticulously redistributed, and its final light, though fading, continues its tireless journey outward, a silent message still traversing the immense stretches of the galaxy. This monumental shockwave, still rippling through the void, might even gently nudge quiescent clouds of gas, perhaps even triggering the birth of entirely new stars, giving rise to future suns and their accompanying worlds. Those heavy elements, forged in the star's core and now flung into the deep, might one day coalesce, seeding the very foundations of future planets. And the countless neutrinos, those elusive, ghost-like particles, they pass silently through everything, through distant planets, through your very body, through every atom of dust, never stopping, never truly